Hey everyone, Mr. Newman here, and today we're going to learn about limits. I'm going to just show you a little bit, an introduction, and we'll do more in future videos. First of all, we're going to consider this function right here. Notice one thing about the function, f of x equals the fraction here, 2x times x minus 1 over x minus 1. Notice that x minus 1 shows up on the top and the bottom of the fraction. And if you recall back to our rational functions unit, that means that there is a hole there. And you can see it in the graph. See the graph down here on the right? That means there's a hole at x equals 1 because it divides out on the top and the bottom. So let's get into this. What is f of 1? Well, you plug in 1 and you get 1 minus 1 in the denominator, and that's 0, which means that the function is undefined. So f of 1 is undefined. However, we can ask the question, well, what would f of 1 be if we filled in the hole? And this is what limits helps us answer. So, I'm going to show you 3 ways to answer this question. One way is going to be using a table. A second way will be graphically, which is what we'll do primarily in the rest of this video. And then the third way I'll show you very briefly algebraically, and that will be more in future lessons. So, first of all, with a table. If I plug in a number really close to 1, that will help me get an idea of what maybe it should be if I plugged in 1, even though I'm not allowed to plug in 1, as you guys see up above. If I plug in 0.9, I get 1.8. Let's move a lot closer. Let's plug in 0.99. Well, when you plug in 0.99, you get 1.98. If you plug in 0.999, you get 1.998. Do you guys see what this is getting closer and closer to? However, if we would actually plug in 1, we would get undefined because we get divided by 0, like just above. So what I'm going to do is I'm going to draw this little arrow as x gets closer to 1, not when it is 1, but when it gets really, really close to 1, our y value gets closer to 2 based on the table, that pattern right there. So this was starting with values less than 1, and you can see on the graph here, you notice I'll make little purple dots that look kind of like where they are, not as precise as they could be. But you notice what's happening, we're sliding up and to the right along the line, getting closer and closer to where that hole is. Now you could probably look at the hole and go, oh, that point right there is going to be 1, 2, and that's how you tell graphically. But I want you guys to be able to see, using a table, also why this is. So let's go from the other side. Let's try 1.1. We're going to try numbers just a little bit bigger than 1, and we're going to slide those back down to get closer to 1. So when you plug in 1.1, you get 2.2. If you plug in 1.01, notice we got a lot closer to 1, you get 2.02. If you plug in 1.001, you get 2.002. So notice what these are getting closer to. If you plug in exactly 1, you get an undefined. You get that the function does not exist there, but as x gets closer and closer to 1, once again, because we're coming from above, you get closer and closer to 2. And because both of these, both coming from the left and coming from the right, get closer and closer to 2, we can safely say that the function at the hole, if we could plug it in, would be 2. Now graphically that looks like this. I'm picking points now to the right and getting closer and closer as we go left and down. And you notice we get closer and closer to that point there, the hole, which is 1, 2. Graphically, it's very easy to see, oh, that the hole right there is on 1, 2. So the output, if we could plug in the hole, would be 2. However, we don't always have the graph, and it's not always situated so nicely and neatly like that. So that's why we also need a table, and ultimately we're going to learn how to do this algebraically. All right, let's look at how we write about limits. Oops. So, first of all, you notice that we have the variable right under LIM. That LIM means limit. The variable x approaches 1 of our function up here. Okay, the value it's approaching and then the function. The way you say this is you say the limit of the function as x approaches 1. Or you could say, read out the function if you wanted to, but you can just say the function here. And what we're doing is we're looking at values really, really, really close to 1, not exactly on 1, just really, really close to 1. and trying to tell how does the function behave as you get really, really close to the value 1, both from the left side, like 0.9, 0.99, 0.999, and from the right side, like 1.1, 1.01, 1.001. All right, so that's how we write limits. Let's look at some limits, okay? First of all, I want to show you guys how you evaluate a limit when the value is not a problem. And I'm going to put a little star here. I think you have a star. That's when our function is continuous near the value. So what do I mean by continuous? I mean there are no jumps, there are no breaks, and no holes. So all these examples right here below, these 6 are not like the one we just did in the graph above. These are all examples that don't have jumps, breaks, or holes around where we're evaluating. So let's look at this first one. The limit as x approaches 4 of x squared. Well, I'm going to write down the blank squared, and because x squared behaves perfectly fine when x is 4, or getting close to 4, there's no jumps or breaks around that area, then I can just plug in 4 to see what the limit would be. I'm going to plug in 4 there, and you get 16. That's because if you were to graph it and look at it, all those values get closer and closer to y equals 16 when x gets closer to 4. And that's actually the value of the function there. So sometimes we can just plug in the value because it's equal to the limit. We're going to look on the back side some examples where it's not continuous, and that's where we have to be concerned. But here, where it's continuous at that point, we can plug them in. Let's do the next one too. You've got the limit as x approaches 4 of 5x. Well, plug in 4 for x and you get 20. So the limit of 5x as x approaches 4 is 20. For the next one, we have a small issue because we're dividing by x, so we want to be very careful if we, you know that dividing by 0 is an issue. However, here the limit is not approaching 0, it's approaching pi. And because all around pi this function actually is continuous, then we are perfectly fine. So we have tangent of pi over pi, and we get 0 divided by pi, which is just 0. So the limit of that function is 0 as x approaches pi. If we were approaching a break, like tangent has lots of breaks in the graph and jumps, or dividing by 0, if we were approaching 0, we'd have to do something differently. But because we're approaching where it's continuous, that's perfectly fine. Let's do the next one. Square root of x. Notice that there is a break because you can't plug in negative numbers, so there's a break at x equals 0. But because we're not plugging in 0 or negative numbers, we can plug in 9 just perfectly fine, and we get the square root of 9, which is 3. All right, so right here, limit of as x approaches pi of x times cosine of x. You plug in pi here, cosine of pi is -1, so we get negative pi. And the last one here, there are no breaks or jumps in our parabola and our quadratic function, so I'm just going to plug in 3, and we get 7 squared, which is 49. All right, so notice whenever the value is not a problem, in other words, when it's continuous at and around that point, we can simply plug in the value from below, where it's at, where x is approaching. Let's now look at situations where the limit does not exist. The limit doesn't exist if x approaches a different number from the left and from the right. So right here on this first one, I drew out the limit as x approaches 0 of the absolute value of x divided by x. This is the graph of that function. Notice that as x approaches from the right, the y value gets closer and closer to +1. But as x approaches 0 from the left, the y value gets closer and closer to -1. So which is it? Is the limit +1 or -1? Well, since we can't choose one, we can't say both, we have to say the limit does not exist. And you can abbreviate that with DNE, does not exist. That's the most common situation where limit doesn't exist. Another situation is where the function increases or decreases without bounds. So here, this graph is our next one, the limit as x approaches 0 of 1 over x squared. You notice as x approaches 0, that's going to be going, on the left side, it's going to be going up forever, and on the right side, it's going to be going up forever as well. So the limit does not exist right there. Now I'm going to put a little star here because there are situations, and it oftentimes depends on the calculus teacher and the class, but there are situations where it's better to say that the limit is infinity here, because the left is going to positive infinity and the right is going to positive infinity. For the purposes of this class, we're going to follow the textbook and go with that the limit does not exist right here. So that is, I just wanted to give you a heads up in case other classes say something differently. All right. Lastly, if f of x oscillates between two fixed values, that means it goes back and forth, back and forth, back and forth. And I'll show you what that looks like here. As x approaches 0, notice what happens to the graph. Where we curve around here, and the graph goes up and down and up and down and up and down and up and down and up and down, and it doesn't actually go, the distance it goes up and down does not actually get shorter. It goes all the way up to +1 and all the way down to -1 every time. So as it gets closer and closer to 0, well, it doesn't get closer and closer to a single value. It's constantly jumping up and down, up and down. So the limit here does not exist either. Those first two are the most common that you will see, where they're approaching different numbers from the left and the right, or it increases or decreases without bound. So be aware of those. I just wanted to show you guys the third one so you can say you'd seen it before. Okay, now let's try some examples of limits. So this first one, notice f of x is the function here, is the graph on the left, and g of x is the graph on the right. I'll do the f of x problems and I'll let you try the g of x problems. So this first one, we say the limit as x approaches -4 of f of x. Well, the limit of f of x as x approaches -4 is right here on the graph, because on the left side we're approaching that value, and from the right side we're approaching that value. So the limit, we're getting closer and closer to the y value of 2. So we're going to put that the limit is 2. However, the function itself at -4 does not exist because there's a hole there. So we need to say that f of -4 is undefined, because there's a hole and it's just not, there's not a value at that point. All right, next, the limit of f of x as x approaches 1. Notice from the left side, the y value is getting closer to 4, but from the right side, the y value is getting closer to -2. So because the left and the right are different, we need to say that the function, or the limit, does not exist. However, the function at that point, f of 1, does exist because there's a filled in point right there at 1, 4. So the output, when you plug in 1, the output is 4. So the function does exist even if the limit doesn't. And notice right here for these first two, you can have situations where the limit exists but the function doesn't. There's no value at that point. And you can have situations where the limit doesn't exist and the function does have a value at that point. So notice that those are different situations. All right, next up, the limit as x approaches 4. Well, notice as we approach from the left and the right, we're getting closer and closer when x is 4, closer and closer to a point here that looks like it's 4, -2. And indeed, because it's continuous there, we can simply look at the exact point and say, yes, that function, the limit as x approaches 4 is -2, because the left side and the right side are both getting closer to -2. The function itself also exists at that point, and it's also -2. So there are times when the limit equals the function. Lastly, notice from the left and the right, as x approaches 6, the limit is always getting closer to the y value 5. So we're going to put a 5 there. However, the function at that point does exist because there's a filled in point down here. It's like a jump just at that one point. So f of 6 is actually equal to 2. So notice one other thing with these last two. You can have the limit and the function be equal at a point. We actually call that continuous when that happens. Or you can have the limit and the function not be equal, but both be equal to something else. So the limit here is 5, but the function itself at 6 is 2. All right, go ahead and try these, and I am going to show you the answers in just a moment. All right, hopefully you tried those. Here we go. The limit does not exist because they're going to approaching different values. However, the function does exist because of the filled in point, it's 2. Here, as x approaches 0, the limit exists, it's 1, and the value is also 1 because the point is right there on the curve. Lastly, the limit here as x approaches 3 is 0 because they both approach the whole 0 there, but the function does exist, and it is defined. It is -1. Thank you for watching.